Hello students, welcome to classroom. I hope you're all doing well, and I also hope that you're taking your studies seriously. So continuing with the lecture, today we will be discussing together the image formation for concave lenses. There are only two cases here, so it will be very much easy. And likewise, in the same video, I will be discussing the lens formula and the magnification. So let us continue with the class now. So image formation cases for concave lenses. There are two cases. Let us straight away start with the cases. Case 1. So in case 1, the object position. Object position means where is the object kept. Then image position, where the image is formed. Then size here refers to the size of the image, and the nature. So let us draw ourselves a concave lens now. So concave lens, do not forget to mark the aperture. For both concave and convex, we need the aperture. Then draw the principal axis, not forgetting to level the optical center. Then let's mark the focus. So let's say my f1 will be this much, then same distance here. So this is my f1, and here will be my f2. Okay, this side f2 to f2, f1 to f1. On the left, f1 to f1. On the right, f2 to f2. Okay, this is my left and this is my right. Now case 1, in both the lenses, convex and concave, the object is kept at infinity. Whenever the object is kept at infinity, we will draw only two light rays traveling parallel to the principal axis. Okay, so let's draw those two incident rays. So let one of them be this, and let the other be this. Okay, so these are the two incident rays. Now remember that concave lenses are diverging in nature. That means these two light rays, okay, after undergoing refraction, they will further split away from each other. They will further increase the distance between them, and they will further diverge away. Okay, in terms of convex, what happens is that these two light rays, they converge at f2. Okay, they converge at focus, they meet. But that will not happen for concave lenses. For concave lenses, after undergoing refraction, okay, the refracted rays will go like this. Okay, they will diverge away. Okay, so how are they gonna meet? Well, they will appear to meet at f1. Okay, that's how it will go. So they will appear to meet at f1. So let us show that like this. Okay, so let them undergo refraction. After refraction, they will go like this. After refraction, they will go like this. So this is how the two refracted rays, they travel. Okay, they appear to meet at f1. So object position at infinity, yes, at infinity. Then image position at f1. At f1, size, point size, is it not? This is point size. In case 1, for convex also it was point size. For both the mirrors also it was point size only. Nature, this is, well, the two refracted rays, they are not meeting actually. They appear to meet. In such a case, what we get? We get virtual image. Okay, and virtual images are all erect. So this is a case of virtual and erect. Virtual images are erect. Okay, so this is case 1. Okay, now we go to case 2. So let us have a look at case 2 now. So let's write the object position. Object position, then image position, then size and nature. So let us draw the ray diagram now. Concave lens, aperture, then the principal axis, and not forgetting to label the optical center. Okay, now what do I have to do? I have to label my f1, f2, to f1 to f2. Okay, so let us take the f1 here. Let me keep it here, then here. Similarly, let me go here now. So this is my f1, and this becomes my 2f1. This is my f2. This becomes my 2f2. Okay, now the object is in front of the lens. Okay, no need to specify where it is. Okay, I've just drawn this to show you. Okay, but then no need to mention where the object is. Okay, just in front of the lens. Okay, just in front of the lens. We don't actually need this also. Okay, we don't actually need this also, but let's just draw in front of the lens. So let the object stand here. Okay, here in front of the lens. Okay, we're not going to write object between 2f1. Object is between 2f1 and f1. No, we're just going to write object position in front of lens. All right, we don't specify where the object is. You can draw it here at 2f1, still correct. You can draw beyond 2f1, still correct. Okay, but do not draw. Okay, but do not draw at f1. All right, so if at all you have to remember something, do not draw the object. Okay, do not draw the object at f1 or between o and f1. Draw behind f1, draw it at 2f1, draw beyond 2f1. They're all correct. So I'm keeping it between f1 and 2f1. Okay, now this is the object in front of the lens. Okay, then as usual, rule 1 goes parallel. Okay, then what happens? It will undergo refraction. Okay, but this is a concave lens, so it's diverging in nature, so it will appear to pass through f1. Okay, so it will go like this. Okay, and the second ray I'll use rule, which rule? Rule 3. Okay, so we'll use rule 3. So rule 3, it will pass through optical center. Okay, and this will go without any deviation. Okay, so this is the second ray. Now this ray continues its journey. Okay, and it's going ahead all the way. Okay, so where are the two refracted rays meeting? Okay, now this ray takes its path. Now this ray on back tracing, okay, we find this point here. Okay, so this point will be considered for case 2, and then the image will be formed here. It's a virtual image, so it will be a dotted line. Okay, we cannot use, don't draw a continuous, don't draw the small arrow in a continuous line, make it dotted. Okay, because it's a virtual image. Okay, so image position, where is this? This is between f1 and o, or o and f1. So image position between o and f1 or f1 and o, anyone. So image position, okay, between f1 and optical center. Size is small. Okay, diminish, we write diminish, we don't write small. The word small is substituted by diminish here. And nature is virtual, and erect, it's an erect image, so it is virtual. Okay, erect image, so virtual and erect. So that's it, class. Okay, these are the two cases for concave lenses. Okay, now we will proceed with the next topic, which is lens formula and magnification. Okay, so let us do that. It's a small topic. All I have to do is give you the formula, and I will not be giving you the sign convention, because the sign convention I have already given you for mirrors, and it's exactly the same. Okay, the same sign convention is followed, so it will be the same. So let me tell you the lens formula now. So lens formula formula. It's 99% similar to mirror formula. There's only one small difference. Okay, now lens formula goes like this: 1 by V, okay, minus 1 by U is equal to 1 by F. This is lens formula. All right, the only difference here is this negative sign. In mirror formula, the mirror formula was like this: 1 by V plus 1 by U is equal to 1 by F. This was mirror formula. So you see the difference between lens formula and mirror formula? Yes, the positive has become negative in lens formula. All right, this is for mirror. This was for mirror. Okay, and then magnification. Now magnification, the definition for magnification still remains the same. Magnification is the ratio of the height of the image to the height of the object. Okay, so magnification formula still remains the same. So magnification has got two formula. Magnification is equal to HI, height of the image, divided by the height of the object. This is one formula for magnification. The other formula for magnification is V divided by U. This is the second formula for magnification. Okay, now there is also a slight change here. Magnification, okay, formula for mirror for the second equation was minus V by U. Okay, now you do not see this minus. Okay, in lens formula we do not have the minus anymore, but in mirrors the second formula has got minus here. Okay, remember that. So this is the second difference between the lens and mirror. Okay, the first one being here, the second one here, you do not see the minus anymore. Okay, now it is positive. So M is equal to V by U. Okay, now comparing equation 1 and equation 2, you will get HI divided by HO is equal to V by U. Okay, this is the formula to find the height of the image, provided height of the object is given to you. You have the image distance and the object distance. Okay, and for any other question where they want you to find the magnification, if you have the height of the image and the height of the object, put the value, divide, you can find the magnification. And then similarly, even if you don't have the height of the image and the height of the object, if you have already found the image distance and object distance, that itself can give you the magnification. So all you have to do is remember this formula. This is very important for numericals. 1 by V minus 1 by U is equal to 1 by F. This is the lens formula, very useful. Then this is another formula which is very useful, and likewise these two formulas are also useful to find magnification. All right, so this is it. I will end the class from here today, and then I hope and pray that you all are learning. Okay, you all are learning. It is my sincere prayer that you all learn something by watching these videos.